Welcome to Electrochemistry, also the last unit of grade 12 chemistry. This is also the hardest unit considered by many students. In this unit, we'll be learning oxidation number, oxidation reduction reaction, galvanic cell, reduction potential, Nernst equation, and electrolytic cell. Let's begin by the definition of oxidation number. Oxidation number denotes the charge of an atom in a compound. There are a few rules to this. The first rule is that for a single element, the element has zero charge. For example, the nitrogen gas and chlorine gas, they have zero oxidation number. The second rule is that the sum of all oxidation numbers of each element multiplied by its numbers in this compound equals to the total charge of the compound. For example, in CH2Cl2, the total charge is equals to 0. If we take a look at each individual element, there's one carbon, 1 multiplied by 0, and 2 hydrogen, 1 plus 1 multiplied by 2 multiplied by 1, and chlorine, negative 1, 2 times negative 1. The sum is equal to the total charge of 0. And there are two extra rules. The first one is hydrogen always have a plus 1 with non-metal and a negative 1 with a metal. Okay. So HCl, Cl here is a non-metal, so H have a positive 1 charge. For OH, it's kind of special. So here, okay, my bad. This one is a bad example. Let's say KH. Okay, let's say KH. Then the H is going to have a negative 1 and the potassium is going to have a plus 1. Number 4, most of the time that oxygen has a negative 2 charge, oxidation number, sorry. For example, in this chromium ion, the oxygen has negative 2, and in this, I don't know. Okay, I forgot those name of the compounds, sorry. But anyway, the oxygen has an oxidation number of negative 2. And let's see some of the common example. We'll be using the element where we know the oxidation number and find the element that we don't know the oxidation numbers in the compound. Let's do a simple example first. In CO2, the total charge is equal to 0. As we mentioned in rule number 4, the oxygen has a oxidation number of negative 2. And for carbon, we don't know. And we equate this equation, then X equals to 4, which means carbon has a oxidation number of 4. Charge is not very correct. Example number 2. Find the oxidation number for nitrogen in ammonium. Okay, rule number 3. The hydrogen has a charge of plus 1. And we equate this equation. X equals to negative 3. Nitrogen has a oxidation number of negative 3. Let's try a difficult one. H3P2O7. The total charge here is negative 1. We know the charge for hydrogen and the oxygen. 3 times 1 and plus 2x plus 7 times negative 2. X equals to 5. The phosphorus is going to have a oxidation number of 5. There are two more definitions over here. Oxidation means losing of electron or increase in oxidation number. Reduction is the opposite of oxidation, gaining of electron but reduced in the oxidation number. In this typical reaction, if we check the oxidation number for each element before and after the reaction, we will observe that some of the elements they have changes to their oxidation number. For sodium, it has increased in its oxidation number, so this is oxidation. For chlorine, it is the opposite. It reduced in its oxidation number, so this is a reduction. Similarly here, hydrogen doesn't change its oxidation number, so there's no reaction over there. But the sulfur has a increase in its oxidation number, so that's oxidized, and the chlorine is getting reduced. One thing to note is that oxidation and reduction, they always appears in pair. One gets reduced and the other will get oxidized in the overall reaction. So they never appear alone. They always comes in pairs, okay? And now let's talk about how to balance a typical oxidation reduction equations. The first rule is just like what you learned in grade 11. All the elements stay the same amount before and after the reaction. A twist now we are dealing with is that the charge before the reaction happens and after the reaction happens should stay the same. And let's check. Those are the numbers of elements for each of the elements, okay? And we find that the number is not changing. The total charge on one side of the equation and the other side is also the same. Now let's do an example for balancing the oxidation reduction reaction. The first step is to add the hydrogen ion and the H2O to either side of the reaction. It doesn't matter which side you choose at the beginning. We will be making necessary adjustment at the end. And then you will be setting the coefficient for each of the compound in the reaction. For now, we just make each of them based on the alphabetical order. The first one is A, the second one is B, and so on. The step number 3 is to use the rule number 1 to create a relationship. The rule number 1 just states that each element is not going to change the amount before and after the reaction. And based on that, we can get different reactions, different equations for those coefficients of the compounds. And step number 4 is the new one. We're gonna make sure that the charge is always the same before and after. We don't need to consider this when we were grade 11 because I believe all of the compounds they are in charge of 0, so the charge will automatically be balancing out. It doesn't matter what coefficient you are picking, so you didn't need to worry about that when we are in grade 11. But now this is an issue because each compound they now have different charges. There are some ions over there. And we have a system of equations. If you know how to solve it, then it should be very straightforward. We will do some basic substitutions, and then if we have a very complicated equation like this, we just manipulate the coefficient and try to cancel out some of the terms, and then do the substitution and get the relationship of a certain coefficient. So in the end, for each of the coefficient, you should be able to express them using the same coefficient. In this case, I pick A. Then you're gonna choose a number for the coefficient that you use to make them to be an integer coefficient ratio. Then you can sub in those numbers back to the original equation. If you see a negative coefficient like this, you just switch it to the other side. It's no big deal. And then just do a quick check like what we did over here. If it's following rule number 1 and rule number 2, to see if the elements have the same amount on each side and make sure that the charge are the same. And you are good to go. It's not something hard, just make sure that you know how to solve the system of equations. Let's talk about galvanic cells. It is a device to convert the chemical energy into electric energy. This is how does a typical galvanic cell looks like. There are two different parts. One part is called the cathode, the other half is called the anode. For each node, there is a metal and there's a solution. The metal is sometimes called the electrode in case the question says, oh, what is the electrode of blah 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 blah? Then you know it's referring to the metals that's attached at each cell, okay? At the top, it is the wire. The currents are flowing from one direction to the other. Here, under the wire, this is the cell bridge. And inside the cell bridge, there's some kind of ionic compound. And it will get dissolved into a positive ion and a negative ion. And they will flow to the two cells. Cathode is where the reduction takes place, and anode is where the oxidation takes place. This is the definition. In this case, in this case, if we assume that metal 1 and solution 1, this is the cathode, then metal 1 and solution 1, they are having a reduction reaction. By contrast, the other one, metal 2 and the solution 2, they are having a oxidation reaction. The wire is responsible for transferring of the electrons. The current is always from the anode to the cathode, because anode is where the oxidation is taking place, so electron will be released, whereas the cathode is where electron is needed for the reduction reactions, so it needs electron inputs. So it will get the electrons from the anode, so the electron will flow from the anode to the cathode. The cell bridge is used to contain non-reactive ions. The ions will move to the cathode and anode to maintain the charge difference in order for the reactions to keep going. If we don't have a cell bridge, what will happen is that the charge will be balanced, and then the reaction will immediately stop. But if we add a cell bridge, it's different. For example, the anode, as we know, it's releasing the electrons and it's transferring to the cathode. The negative ions from the cell bridge comes into the anode for this to for it to maintain a negative charge, and the cathode to maintain a positive charge for the positive ion that goes into the cathode. That way we will keep having a charge difference, and when the reaction is going to be stopped is when one of the reactants in the overall reactions are running out. For example, if this is our overall reactions, as you can notice, the charge on each side is the same, and for each element there's the same amount on each side. The cathode is going to be the reduction half of reactions. The anode is going to be the oxidation half of the reaction. Let's do an example. We can also, based on which one is having the reduction, which one is having the oxidation, we can determine which one is the anode, which one is the cathode. In this case, we can see copper is having a reduction. as we mentioned before, reduction is equals to the cathode, and anode is always equals to the oxidation. So copper is the cathode and Zn is the anode. Let's talk about the standard reduction potential. This is the symbol for indicate that quantity. It allows us to compare and find which element is more likely to get reduced. The higher the electric potential, the more likely it is will get reduced. For example, here we have two different reduction reactions. Each one of them is given a reduction potential, and we need to determine which one will get reduced. We simply pick the one with the higher reduction potential, because we know that the higher the value, the more likely it will get reduced. In this case, the fluorine will get reduced. It has higher value. The cell potential is just the difference between the two nodes, okay? The cathode reduction potential minus the anode reduction potential, it is just the difference. If we use the example that's above, then this cell is going to be having a cell potential of 1.78. We take the reduction potential of the cathode and then reduce the electric potential of the anode. We get the difference. It's that simple. Let's talk about a bit about thermodynamic favorability. I know it has been a very long time since last time we see the Gibbs free energy, but there's a formula that's related to this. So the delta G is equals to negative NF E cell. N is the number of moles of electrons that's in the overall reactions that's being exchanged. F is the Faraday's constant. This is a constant number. E cell is the cell potential. Delta G is the Gibbs free energy, which is we learned from a long time ago. If E cell is greater than 0, then delta G is less than 0, which means it is thermodynamically favored. If this is less than 0, then delta G is greater than 0, which means it is not thermodynamically favored. For galvanic cell, E cell should always be greater than 0, because imagine this. The definition of galvanic cell is where chemical energy is converted into electric energy. So the chemical energy is going to sustain itself and let it keep going by itself without any inputting any other source of energy, and converting that to electric energy, which is the transferring of the electrons during the process, okay? And that's how we get the delta G is greater than 0 if the E cell is greater than 0. Let's do a quick review to see what kind of problems you will be seeing for your chemistry course. And here is a diagram of a typical galvanic cells again. And based on this diagram, we need to figure out a variety type of questions. First, which metal will get reduced? We just need to pick the metal with the higher reduction potential. In this case, copper has a higher reduction potential. So copper will be the one that's getting reduced. Write the two half reactions. We just need to take a look at what solution are there and also what is the metal. And then we can observe the number of electrons that's being exchanged for each of the pairs that's in here, and we just write the reactions. Since we know which one is getting reduced, so there's no doubt for which side is the ion and which side is the metal itself for each reaction. Determine the anode and the cathode. once we figure out which one is getting reduced, which one is getting oxidized, we can easily figure out the cathode and anode. And question D, the direction of the current. The current is always from the anode to the cathode because anode produce the electrons and cathode require electrons. So the electron will be transferred from anode to cathode. So question E, what is the direction of the positive or the negative ions? So in this case, if we take a look at the diagrams, the positive ion will go to the copper cell, which is the anode. Okay, sorry, my bad. Well, goes to the copper cell, which is the cathode. Yeah, cathode. The positive ion will go to the cathode to balance the charge due to the added electron, while the negative ion will go to the anode to replenish the loss of the electrons. So the last one, which electrode or the method will increase in size. If we figure out each of the half reaction and figure out which one is getting reduced, which one is getting oxidized, we just need to observe the product. So in the one that's getting reduced, copper metal will be produced. So the metal copper will increase in size or increase in mass, whatever. And so zinc will be used up, so that one will reduce in size instead. Let's take a look how to calculate E cell in non-standard condition. There's an equation for that, but most of the time you probably don't need to know the exact calculation to decide whether a cell will last longer or shorter. But it is very good to know and also know how to do the calculation. This equation is called the Nernst equation. Here, RT is just like how you use ideal gas law. R is the ideal gas law constant. The one with 8.137, and the T is the temperature in Kelvin. N is the number of moles of electrons that's being exchanged in the reaction. F is the Faraday constant. Q is our friend, the reaction quotient. So this one is the E naught cell, which is the E cell that we have been calculated before. So we assume that E cell is in the standard condition, which means that the temperature is 25 degrees and the pressure is 1 atmosphere. And also, for each of the solution in each of the half cells in our galvanic cell setup, they are all 1 mole of concentration. And in that case, E naught cell is equals to E cell because long Q is just going to be equals to 0, and that thing just equals to 0, and those two terms are equates to each other. And here we will be focusing on how to calculate the E cell, the cell voltage in non-standard condition. So one thing here is if Q is greater than 1, then long Q is going to be greater than 0. As you can see that E cell is going to be less than the E naught cell, so the galvanic cell will last shorter. By contrast, if Q is less than 1, then the cell will last longer. And let's take a look at one example. The question will give you the reaction and tell you the concentration of each of the ion component, and let you decide whether the cell is going to last longer or shorter. What you're gonna do is to find the reaction quotient. Here we only cares about the ion. The solid does not take into the account, it doesn't matter. And we sub in our concentration and see if the Q is greater than 1 or less than 1. And we can make a judgment. In this case, this Q is greater than 1. So the cell will actually last shorter. let's review how do we do most of the calculations so far. So the first thing is to make sure you know what is the reaction that's happening. Like this question, we are given two separate half-cell reactions. We combine them together. First, we just follow the procedure that we talked about before. We compare the reduction potential for those two reactions, and we find the higher one to be the reduction reaction, the other one to be the oxidation reaction. And then we have our balanced equation. So usually these questions will have very simple reactions, so you don't need to worry about how to balance the charge equation. Usually it's not too hard. Then you just make sure that they are exchanging the same amount of electrons. If not, you just manipulate the coefficient and make sure that they are having the same electrons exchange. Then you're gonna calculate the E naught cell and the delta G. The E naught cell is just going to be the higher one, subtract the lower reduction potential, and we get the difference to be our E naught cell. The delta G, we use this formula. Delta G equals to negative MF E cell. And we sub in the number of moles of electrons getting exchanged, the E naught cell value. This should be E naught cell. And the Faraday constant, we multiply that, we calculate the delta G value. And how do we figure out the E cell is to first take the E naught cell and subtract the other half of the Nernst equation. We calculate the reaction quotient, we sub in. This one is constant, and we sub in the temperature we are given, the number of moles of electron, and the Faraday constant, and we calculate it. Usually this one should be smaller because as the reaction is going, the product is going to increase in concentration, while the reactance is going to decrease in concentration. So the E naught cell will have a less voltage difference, which means the cell is going to function in a shorter period of time. This one should not be too hard. As long as you remember this equation, I think you can figure out most of the problem. Now, this is the final topic of the whole unit. We will be talking about the opposite of a galvanic cell, which is the electrolytic cell. Unlike the galvanic cell, electrolytic cell use the power source to drive an unfavored reactions from happenings. This is very useful when you are charging a battery or you are producing aluminum, metal. This is very practical in real life. And let's take a look at different components of a typical electrolytic cell. At the top, here is the power source, which is driven the whole reactions going, connected by the wire. It is connected by the wire with the two different electrodes, the two metals. One is the anode, one is the cathode. And now you can notice that the whole thing is in a single bottle of water. No, like a big jar. They are no longer separated. The anode and the cathode, they are in the same solution. The negative ion is close to the anode, and the positive ion, the cation, is going to the cathode. Not a lot of difference, except now they are no longer separated and there's a power source. Cathode and anode, the definition still the same. Cathode is where the reduction happens. Anode is where the oxidation happened. The current is still flowing from anode to the cathode. Remember, cathode is where reduction happens. It needs electron, and anode gives away the electrons. The ions cation to cathode, anion to anode. Just like before, it does not change. Now let's take a look at what do we need to do in order to decide what reaction will happen in each of the half cells. We are given a list of possible reactions. The first thing you do is to see if the reaction is actually valid and there is enough reactants for this reaction to happen. In this case, we are having the NaCl solution. We will notice that this reaction, 2H plus 2 electrons, this reaction is impossible because in the solution there is no H2 ions, or we can say it's very little, so it will not be our main reactions over here. So we cross that out. For the rest of the reactions, we just need to pick the one with the highest reduction potential, which is the water. So this water plus 2E minus is going to be our reduction reaction. For the anode, we do the same thing, except now we are given the oxidation potential. If you don't know, the oxidation potential is just the opposite of the reduction potential. We also pick the one with the highest value. We cross out this one because there's little OH minus ion. For the rest of them, we pick the one with the highest oxidation potential. So this one is going to be our oxidation reaction, okay? Because it has the highest oxidation potential. For a reaction, if you flip the reaction, if you are beginning with an reduction, you flip it, then it's going to be the oxidation. The reduction potential is going to change into the oxidation potential. There will be also a new negative sign over here. The reverse is also true if you begin with a oxidation reaction and you now change it to a reduction reactions. You get from oxidation potential to reduction potential, and you also flip the sign of the value. This is just one simple example. Now, if we are just given a single solution, which is where the electrolytic cell happens, now we first list out all of the possible reactions. These are the reactions that I copied from the reduction table. And then we're gonna discussing the reactions take place at each of the half cells. We begin with the cathode. These are the possible reactions. Note I didn't pick this one because we don't have oxygen. And you almost never need to consider this because of the reduction value. So in a normal case, this one will be the oxidation reaction. This one will be the reduction reactions because we'll be looking at the side where the water exists. We use the same procedure, except now we just figure out the reactions by our own. We cross out the impossible reactions where the substance doesn't exist in the solution, and then we pick the one with the highest potential. Now we just flip the size of the reaction. Notice that they are all reductions. Now I flipped some of them, and then they become oxidation reactions. We also flip the signs of the reduction potential to get the oxidation potential. We cross out the impossible reaction, then we pick the one with the highest oxidation value. and we get both of the reactions. Okay, finally, this is the final equations we need to learn for the whole unit, which is the Faraday law for electrolysis. The first one is going to be a new reaction. New equation, sorry. N1 is the number of moles of a reactions that take place, and N2 is the moles of electrons that's being exchanged during the process. And here, this thing is the Faraday constant. It's just a constant, so you don't need to worry about that. Okay, maybe I should say not per reaction, per moles of reactions to be more accurate. And Q is the total charge. For some of you may have seen this equation already because you took physics. When you took the grade 11 physics, you will see this equation when you are learning about the circuit, the parallel circuit, and the, what is the name of the other circuit? Series circuit. Sorry. It has been quite a while since last time I learned anything about physics. But that's not important. Anyway, we are learning about chemistry now. There isn't much different types of questions that you'll be seeing. You are given almost all of the values that's here, and you will be finding one unknown value. For example, in this case, we need to find out the time. We rearrange of two of these equations, and we get a whole terms for this. And if they did not directly tell you the moles of reaction that take place, what you need to do is to divide the mass by the molar mass to get the moles of substance, and sub that in and calculate the time. Here is another example. You will be calculating the mass that will be produced if you are given all other things. This is our original form of the equation, and you multiply the molar mass by both sides, and you sub in the value, and you get the answer. It's pretty straightforward, actually. And that's the end of the electrochemistry unit. And good luck with your AP chemistry study. This is the end of the whole course. I'm so happy that you made all the way here. Good luck with your chemistry. Bye.